Chapter 4, Lesson 1 of Pre-Calculus, continuing to discuss angles and measure, and a couple of applicational things that we want to look at as we introduce this video. When we talk about navigation, the course or the bearing of an object is sometimes given as the angle of a line of travel measured clockwise from due north. Now this is especially important when we're doing, again, navigation problems, when you're reading a word problem. And we need to understand that when we're talking about a course or a line of bearing, that's always or usually measured from a due north. In other words, if you're facing north, and I said we were traveling at 100 degrees, then how do you know where I'm traveling? Well, the line north would be one side of the angle. You would then measure 120 degrees, and the direction that arrow is now pointing, that would give you the bearing or the course of the ship or whatever it is that you're talking about in navigation. Now this is especially important to understand because when we start talking about trigonometry in the next chapter and lesson, the trigonometric angles are going to be measured from the x-axis, which would be a line points east. So when you go to convert measurements about bearing, and we use trigonometry to do that, we're going to have to remember to make that adjustment. Now, in this lesson, you won't have to worry about that, but I just wanted to make you aware of that moving forward. The second thing we wanted to talk about before we move further is the fact that since a central angle of 1 radian always will intercept an arc that's 1 radius in length, then it follows that a central angle of any number of radians in a circle with a radius r will intercept an arc that's equal to that number of radians times the length of the radius. So what that does is that gives us this little equation where s is the length of the arc on the circle, r will be the radius of the circle, and then theta will be the measure of the angle. Now the only caveat here is that this angle must be in radians. So if you're given the measure of the angle in degrees, you're going to have to use your unit multiplier and convert it before you can find the length of the arc. So really quickly, let me give you a picture of what that is. So the application of that would be, let's say we have this arc here that's equal, or this radius that's 4, and let's say that this angle we know is 3 pi radians, 3 pi over 4 radians. What would be the length of the arc? So what I'm looking for is the length from here. If I was to walk along the arc, of course, I could walk, I could stay on the line there and walk. How far would that length be? So that would be the s in our equation. So s, the length of that arc, is equal to theta, that's the measure of the angle in radians, which this is. So that would be 3 pi over 4 times the radius, which in this case is 4. So if I multiply these together, these reduce, so the length of the arc is 3 pi units in length. Actually, I said I was going to do this in another video, but I'm just going to add it on at the end here. So let's take a look at angular and linear motion. The problem here is angular speed. If you're talking about that, you're talking about something in revolutions per minute. In other words, you're talking about something going around in a circle. So like a tire revolves, or an engine revolves, RPMs. So angular measurement or speed is measured in revolutions per minute. Linear speed is measured in miles per hour. How far linearly did you go in a certain amount of time? And what we want to be able to do is to convert either from linear speed into angular or angular into linear. The problem is we have to get from something going around in a circle to something going linearly. And so we need some kind of unit multiplier that converts that. So let's talk about that real quickly. If you think about something going around, it's going around in a circle, and what's the distance around a circle? Well, you remember from geometry that the distance around a circle is called the circumference. So if you knew what the circumference was, then you'd be able to know how far it went linearly. In other words, if we have a radius of 1, a small tire, radius of 1 foot, 1 inch, whatever, how far would it go linearly in one revolution? Well, that would be equal to the circumference. So 1 times, pi, or 2 pi r, which would be 2 times pi, that would be how far it went linearly in 1 revolution. So we can use the fact that the circumference is once around the circle. And if you think about what we just talked about, radians, how many radians are there in once around a circle? Well, you remember there's 2 pi radians once around the circle. Pi is 180 degrees. 2 pi would be 360 degrees, so 2 pi's would be once around the circle. So we can take a revolution of 1 and use that as a unit multiplier because it's 2 pi around the circle. So 1 revolution, oh, sorry for that, I didn't convert that yet, but this would be, well, you know what, I'm going to stop the video, I'm going to fix that, and then I'll be right back. Okay, now we're back. So 1 revolution is 2 pi radians, so I can use that as a unit multiplier. 1 revolution is equal to 2 pi radians, and then I can simply use this unit multiplier. If I want radians to go away, I put it like this. If I want revolutions to go away, I just flip it over. So 1 revolution is going to be equal to 2 pi radians. 1 radian, you remember, is the radius of a circle. The circumference is once around, so the circumference is going to be equal to 2 pi radians as well. So if I told you the circumference of a certain tire was 14 feet, well, the circumference, 14 feet, once around, is the same as 2 pi radians. Well, now I have a unit multiplier that I can use to start converting that from the linear into angular or vice versa. All right, so remember that the circumference, whatever that value is always equal to 2 pi radians, so you can set up a unit multiplier. This circumference is once around a circle, and this 2 pi radians is once around the circle. So in essence, I have 1 over 1, so I'm multiplying by 1, I'm not changing anything. All right, same thing here. This is once around the circle, this is once around the circle, so it's 1 over 1. We're not changing the value, we're just using this to help us convert. So let me do one problem for you and show you how this is going to work, and then we'll wrap this up. So in this example, we have Albert's truck has wheels that are 36 inches in diameter. If the wheels are rotating at 630 revolutions every minute, then what's the speed in miles per hour? So what I need to do is take this angular measurement, which is revolutions per minute, and I have to convert it into a linear measurement, miles per hour. So I take 630 revolutions per minute and I set it up as a fraction, 630 revolutions per minute. And the way I think about this is, first I'll do the numerator and convert it, and then I'll do the denominator and convert it, or vice versa, it doesn't matter. So I'm going to do what's easiest. I need to go from minutes, and I need to put it in miles per hour. So I need to convert minutes to hours. So I need a unit multiplier that does that. Well, I know that there are 60 minutes in 1 hour. So again, this is 1 hour, this is 1 hour. It really is simply a unit multiplier. We're multiplying by 1, but it's going to allow me to reduce the units. So the minutes reduce with the minutes. And now what do I have in the denominator? Hours. So my hours are done. I have now revolutions per hour if I multiply this out. So I don't want revolutions per hour, I want miles per hour. So now I have to concentrate on converting this revolutions into a linear measurement. Now that I have the hours taken care of, I want to concentrate on the numerator, and I need to convert revolutions into miles. Now, my unit multiplier needs to have revolutions in it if I want it to reduce, and the revolutions have to be in the denominator. So I need to use 1 revolution, and I need to convert that into a measurement of length. Well, I know that circumference is a length if I can figure out what that is. Well, the circumference, we have to remember, is the pi times the diameter, or 2 pi r. I'm given the diameter, that's why I chose to use this. So the circumference for this particular wheel is pi times a diameter of 36, so 36 pi. So the unit multiplier I want to use is 36 pi, that's once around the circle inches, and 1 revolution, that's once around the circle. So I'm going to use 36 pi inches is 1 revolution. And now the revolutions reduce, and so now I have inches per hour. And what do I want? Miles per hour. So now I need to convert inches into miles. Well, I can't do that, but I can go from inches into feet, and I know that there are 12 inches in 1 foot, and I put inches down here so the inches reduce. Now I have feet per hour. Well, I don't want feet per hour, I want miles per hour, but I know that there are 5,280 feet in 1 mile. This is 1 mile, this is 1 mile. The feet reduce, and now I'm left with units, miles per hour. So I have all of the units taken care of, so now I just have to multiply through. So I have this 60 times this 630 times this 36 times 1, oh sorry, the feet are reduced, miles, that takes care of my numerator, and then my denominator is 1 times 1 times 1 times 12 times 5,280, and then I have hours as my unit. So I have this is my miles per hours, and then I would just calculate that out. So you take this from 1 unit multiplier at a time, and again what I usually do is I concentrate on converting one and then the other. I'll do the numerator first and do all the conversions and have my numerator units correct, and then I'll go and do the denominator. Alright, the key is getting a linear measurement along with a angular measurement in a unit multiplier so that you can convert it from one to the other. Now this will change every problem. Why will this change every problem? Well, because the circumference is going to change in each problem. So while it's still 1 revolution, the distance that's traveled in that 1 revolution is going to change when the diameter or the radius of the circular object changes. Alright, so that's all we're going to cover in this lesson, so we'll wrap this up and we'll look for you when we get into Chapter 4, Lesson 2.